Welcome to Real Civil YouTube channel. In this video, we are going to solve one numerical which will be the application of the response spectrum. So first I will read the question. So this is the question. A one-story reinforced concrete building. So the figure is given like this. So there is one frame, okay, is idealized for structural analysis as a massless frame supporting a dead load of 5000 kg. So here 5000 kg is the mass at beam level. Okay, so this is our beam level. The frame is 8 meter wide and 4 meter high. So here you can see this is 8 meter and the height of the structure is 4 meter. Each column clamped at the base. Here the meaning of clamped is fixed. Has a square cross section of 25 centimeter. That means this column is a square column having 25 centimeter cross section. The Young's modulus of the concrete is given 20 GPa and the damping ratio of the building is estimated as 5%. If the building is to be designed for the design spectrum, so here you can see this is the design spectrum. I will explain you how to use this, and it is scaled to peak ground acceleration of 0.5 g. Okay, I will explain this also. So this is our problem, and we have to find two things. First one is the peak displacement. This is the thing we want to find, peak displacement, and second thing is peak equivalent static force. Okay, so second thing is peak equivalent static force. So these two things we need to find out. For this, we are going to use this response spectrum curve. Okay. So if you see on the x-axis, there is a time period, right? So we have to find first the time period. Okay. So for finding the time period, okay, we know that Tn is equal to 2 pi upon omega n, where omega n is square root of k upon m, right? As you can see here, there are two columns, C1 and C2, right? So we need to find the equivalent stiffness K, which will be equal to 2 times K, because this is in parallel. You can watch our video on series and parallel also. The link is in the description box. So as the columns are fixed, the equivalent stiffness K or stiffness K will be equal to 12 EI upon L cube, right? Now, if you see here, this is E, which is directly given. This is the length or height of the column, which is directly given, right? So, we need to find the moment of inertia. So, I is equal to a raised to 4 divided by 12, as it is a square column. Okay, if it is rectangular, we can use for BD cube by 12, circular column. Those formulas are known to you, right? So here I can write it is 25 centimeter, right? So 25 raised to 4 divided by 12, right? So we will get the answer 3255.08 centimeter raised to 4, and we will convert this into meter raised to 4. So 3255.08 into 10 raised to minus 8 meter raised to 4. As this value is in centimeter, our first calculation is centimeter, so I have converted this, right? Now let's find out K. So K is equal to 12 into modulus of elasticity is given 20 into 10 raised to 9 GPa to Newton per meter square into I is just we have calculated 3255.08 into 10 raised to minus 8 12 EI upon L cube. So we will get the value of K, okay, or we can multiply it by 2 so that we will directly get the K equivalent. So K equivalent will be 2.4414 into 10 raised to 6 Newton per meter, right? So this is our K equivalent. In the problem, they have given mass equal to 5000 kg, right? So I can calculate omega n is equal to square root of K equivalent upon m. Okay, so let's put the values here. 2.4414 into 10 raised to 6, mass is 5000. So we will get the frequency 22.097 radian per seconds. Sorry, per second. Now the time period Tn is equal to 2 pi upon omega n, that is equal to 2 pi divided by 22.097. So I can write here the time period 0.2843. So this is our first step to calculate the time period. Now we can use this response spectrum, right? Our time period of this frame is 0.2843 seconds, right? So where will it be? So we have to use this chart. So here it is 0.66, right? Here it is 1 by 8. So surely this value will range between these two values, right? So I can say that the pseudo acceleration will be 2.71 into, here you can see it is scaled to peak ground acceleration of 0.5 g. So multiply this acceleration by 0.5 g. It is a scaled value, right? So this is how we can use the response spectrum curve, right, to find the pseudo acceleration. Now how to find the peak displacement, right? So we have learned the formula that x double dot max is equal to a omega n square. This simple formula we can use where this is acceleration, this is peak displacement, and this is our frequency. So I can write a, that is peak displacement, equal to x double dot max upon omega n square. So I can say here you can see peak acceleration is 2.71 into 0.5 into g, that we have got from response spectrum. G we know that it is 9.81 divided by omega n square, that we have find out 22.087. Here it is square, right? So if you solve this, you will get the displacement 0.0272 meter. So that will be the peak displacement of the building if there is this type of acceleration is going on. Okay. Now second thing they have asked, this was the first thing, and now the second thing is peak equivalent, peak equivalent static force. So we know that force is equal to mass into acceleration, right? Or mx double dot. Here mass is 5000 multiplied by the acceleration, that is 2.71 into 0.5 into 9.81. So we will get the static force 66.46 kilonewton. So this is how you can use the response spectrum, okay, of a location to find out the forces, movements and stresses coming on the structure. Right now in this problem we have calculated the displacement, force. Now you can again calculate the movement also, okay. Also you can calculate the stresses if the section modulus is known to you. Okay, so this is the application of the response spectrum. I hope the question is clear. If there are doubts, feel free to ask. I will surely reply. Okay, so thank you for watching the video. Please like, share, subscribe the channel. Thank you. Thank you so much.